prime over M, and you're using J plus J prime as a member of the group, because the ordinary group of residues is a group under addition. But now our group is a group under multiplication, the reduced residues. So the analog of just using the simple roots of unity will be the characters which are going to have this multiplicative structure to be compatible with the reduced residues, but at the same time they are also roots of unity, but they are roots of unity of order phi k. Okay, so that's where we're going to come. So we're going to use some orthogonality relations to select integers and specific residue classes. Okay, but next thing that we have to do is a crude upper bound. First, a crude upper bound. How many characters do you have mod k? So that's a question. Okay, question. Very natural question. How many characters do we have mod k? Well, I'll be very crude. So let us look at the set S sub k of all characters mod k. Set of all characters. We will show very soon that that set also has size phi of k, that there are phi of k characters mod k. Okay, so it's sort of another copy, not a copy, but it's a group which is related to the original group. It's called the character group, the collection of characters. But first let us get a crude upper bound. There are phi of k residue classes modulo k, and each value of the character is a root, a phi kth root. Therefore, at every position there are phi k choices at most, but the choices are not totally independent. If I know phi a, I know phi a squared. But crudely speaking, the size of Sk is no more than phi k to the phi k. Now you will tell me, sir, this is totally stupid. I only need in the following proof that Sk is finite. And then once I know the finiteness, I can prove from that Sk is actually equal to phi k. But first I need to know it's not an infinite set. So this is just a crude upper bound. But it shows the finiteness, which is what I need. Okay, so now let us move on to proving some theorems. All right, so now sequence, theorem 3. Theorem 3 is that chi be any character. Okay. Then, if I sum this character or all the values of the group, we can even put a and zk, it doesn't matter, because this sum is really a and zk star, right? Zk cross. Then this is equal to phi of k if chi is the principal character, and it is equal to 0 otherwise. Okay. So if I take, so this is the analogy of the sums of the roots of unity. So you take any root of unity and take its powers, that will give you n, they are nth roots of unity, if you start with 1 as the root of unity. But any other root of unity will give you 0. So this is analogous. And so then I put phi of k. So proof. So clear if chi equals to chi 1. Because chi 1 means this is so let chi be not equal to chi 1. So the moment you have a non-principal character, it means there is some number m at which the value of this character is different from 1 and non-zero. M equal to 0 doesn't work. All right. So there exists m relatively prime to k such that chi of m is not equal to 1. Now we use the following property. We use the following property that the the set M times A, where A runs through zk cross, is once again zk cross. So if I take the reduced residues modulo k, I just multiply every reduced residue by a fixed M, which is a reduced residue, I get back the set of reduced residues in some order. Okay, thus, this sum, A belongs to zk, is precisely the sum